Hey everybody, Dr. Retzik here. This is our fifth of 6 videos in section 7a. Let's get started. So far in 7a, we have considered this situation where you got an inner product space and you got a map T that takes inputs from that inner product space and produces outputs in that inner product space, and you can always form what's called the adjoint to that map. The symbol is T star, and that mapping that runs right to left called T star, that's guaranteed by Riesz representation theorem, and sometimes it equals T and sometimes it doesn't. When T equals T star, T is called self-adjoint. I'm starting to feel like 7a is turning into kind of just a litany of theoretical facts and statements of things with sort of technical hypotheses. And I thought maybe we could just do an example today. Just an example. So here's an example. In this example, things are very concrete. The box serving as our inner product space, that's R2. And T maps R2 to R2. And T has a very, very specific formula. So let's say T of x comma y spits out 3x plus y comma negative x plus 3y. All right, so that's a perfectly reasonable linear operator from R2 to R2. Okay, let's see if we can figure out its adjoint. All right, so let's see what happens here. So we're interested in what happens when you do the inner product, standard inner product in R2, good old dot product. What happens when you do the dot product between txy and, say, some other vector, ab? Okay, well, we can figure this out. The formula for txy is right there. So this is 3x plus y comma negative x plus 3y inner product with ab. Okay. And then we know how to do dot products. So this is A times 3x plus y plus B times negative x plus 3y. It's just dot product. Okay, cool. Now, you could rearrange this as x times, what, 3a take away b, plus y times a plus 3b. In other words, the inner product we started with is equal to this inner product, x comma y with 3a minus b comma a plus 3b. And that means that this quantity here, that is T star of AB. It has to be, because the defining property of the adjoint is when you do T vector comma other vector, that's supposed to be the same as original vector comma t star of other vector. So we have a formula for t star now. We've actually determined a formula for the adjoint. Now, if you didn't want to go through that sort of mechanical process of figuring out what t star of AB was, you also could think about the matrices for the mappings. So with respect to ON basis 1, 0, 0, 1, so that's the standard basis in R2, you could just figure out the matrix for T. And the matrix for T is, okay, well, first column, you got to see what T does to 1, 0. So scroll up. What does T do to 1, 0? Gives you a 3, negative 1. And what does T do to 0, 1? It gives you a 1, 3. Okay. Now, because we're working with an orthonormal basis, then for free, you get the matrix for T star simply by taking the conjugate transpose of the matrix for T. Now, the conjugate part in this example doesn't mean anything because all of these are real numbers. This is happening in R2. So really, just transpose. And if you take the transpose of that matrix, that means switch who's playing the role of rows and columns. So first row used to be 3, 1. So now first column, 3, 1. Second row used to be minus 1, 3. So now second column, minus 1, 3. So that transpose, you just kind of flip it across the diagonal. So you see the diagonal entries, they stayed the same, and the diagonals above, or entries above and below the diagonals just swapped. Now what you can see here is that this is not the same as M of T. So the matrix for T star is actually different from the matrix for T. So the grand conclusion in this example is, therefore, T does not equal T star. If they were equal, they would have the same matrix, i.e., T is not self-adjoint. Okay, so here's an operator that is not self-adjoint. Okay, fine. Here's what's interesting, though. Check this out. If you take the matrix for T, which was 3, minus 1, 1, 3, and multiply it by the matrix for T star, which was 3, 1, minus 1, 3. Let's see what we get. Well, it should be 2 by 2 again. Let's just figure out the entries, like old school, Math 206. So 9, 10. Negative 3 plus 3 is 0. Negative 3 plus 3 is 0. And then 1 plus 9 is 10. Oh my, okay, interesting. Fluke? Time will tell. If you do it in the other order, though, so you do the matrix for T star times the matrix for T. I mean, we have to do it out. There's no reason to expect it to be the same matrix because matrix multiplication is not commutative. So matrix A times matrix B, that's not the same as matrix B times matrix A in general. So we got to multiply it out. So it'll be 2 by 2 again. Let's see what happens. 3, oh, 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 oh my goodness. They match. So T star is the same as T star T, even though T and T star are not the same. In other words, this mapping, this thing we're calling T, it commutes with its adjoint. So you can multiply T and its adjoint in either order and you get the same answer. This leads to a definition. That's quite the lucky fluke. Definition. An operator T acting on V is called normal. That's the word we're defining. If TT star is the same as T star T. That's what it means to be normal. We have a concrete example here of a normal operator. So this linear operator right at the start, we just decided that this T right here is normal. Now, the question becomes, is there a way to tell this without sort of computing T and its adjoint and multiplying them together in both orders and comparing? Is there some characterization of normal operators? Certainly in the 2 by 2 case, it's easy to characterize. And all of that is coming. For the time being, normal just means not quite self-adjoint, but still pretty good because TT star is the same as T star T. And one thing that you're going to discover as you read on and finish section 7a is this. Anytime T is normal, from V to V, all right, T star runs this way. If T is normal, like why the word normal? That seems, I don't know, suggestive. Normal, you mean like are other operators abnormal? Like what is going on here? Here's one sense in which T is, quote, normal. If T is normal, then when you take a V, which remember is on both sides of this picture, if you take a V and you do T to it, you just get some other vector in big V. Or if you do T star to it, you just get some other vector in big V. Now, self-adjoint means those two vectors are the same. Literally the same, because T and T star are the same mapping. Normal says, all right, yeah, fine. Not exactly self-adjoint. So it's not true that TV equals T star V necessarily, but all is not lost. This is true. The norms match, and that's the sense in which T is normal. The norms stay the same, whether you go left to right or right to left. The norms match, and in fact, that's actually an if and only if. And that will be one of a little suite of concluding facts about normal operators at the end of 7a. 7b serves as the justification for the existence of 7a. Right now, 7a might seem a little out of nowhere or potentially not good for anything. Why are we talking about self-adjoint? Why are we talking about normal? Why are we talking about adjoints for that matter? We will be vindicated in 7b. So be patient, work on that weekly homework, and I'll see you next time. Bye.